Alright, what's up guys? Today we're gonna be solving snapdragons. So basically this is a relatively easy problem even though it's in the challenge category, but what we're gonna do is show you the difference between elegant and brute force approaches to this problem. So let's start. Here's the problem statement. Let's open up Paint and I'll explain. Basically, there is one dragon, Rose. We'll call it Rose R, and a dragon Scarlet S. Basically, Rose has a certain number of cards, and Scarlet has a certain number of cards. And what they're trying to do is they write the numbers on all of these cards at random. Then they play a game of snap. That is, they place one card down, and whatever card matches. If the card matches, then the first one to say snap wins. Basically, what we need to do is find the number of possible snap pairs that there are, all possible snap pairs. So we have the first one. If you look at the input, the way it's inputted is that the first, so you give an R and S, and the first R lines give you Rose's cards, and the following S lines give you Scarlet's cards. So here we have for Rose 6, 4, 2, 4, and we have 9, 2. Alright, a simple approach would be to look at the cards, and we can see 6, there are no 6 cards, so automatically there's no 6. There's a 4 here, there's a 4 here as well, but there's no 4 in Scarlet, so there's going to be no snap pairs there. But we have a 2, but we also have a 2 here, that makes 1 pair, so the total number of pairs equals 1. And then another 4, which we don't have, so the answer here should be 1. Basically, the theoretical side of this means that, so if we let X be number of cards Alright, so basically, if we have, let's say, let X be the number of cards for Rose of a certain type, let's say. So, we have X amount of 8 cards, and we have Y amount of 8 cards for both Scarlet and Rose. Now, theoretically, our answer should be just the amount of X cards for Rose times the amount of Y cards, and we plus that to an answer variable. Okay, so that's the base theoretics done. Now let's move on to how we're gonna do it. So obviously the best way to start a problem like this is to go for a brute force approach. The brute force approach would be basically we append all of Rose's cards into a list, and then we append all of Scarlet's cards into a list, and then once we do that, we can iterate through both lists and see the similarities between them. So we have R equals, we'll use the first sample, sorry, that's the list, and S would be S would be 9, 5, 2. So now once we got our list set up, basically the algorithm would look like something like this. We will look, so we would look at, let's say our list for example. So you know what, it's actually going to be easier to write it like this. So let's say we have R defaulted to what? Sorry, 6, and S would be defaulted to 952 2. So basically set an answer to 0 for I and R if I in if I is also in S, then we answer equals plus equals R dot count I times. Alright, basically this is our base program. So we iterate through this and this, and if the 2 is the same, find our if I is in S, so we got the 2 in S as well, then the answer, and then we look at the amount of times the 2 appears, then we times them, then we plus our add it to our answer. So if we print, yep, that's 1. And if you go to the sample test case, the answer is 1. Now we'll try with another one. 8, 9, 9. Okay, R equals it. And this is what? 8, 9, 9, 9, 9. This is 9, 9, 8, 9, 9, 9. Alright, now we've got these two. Basically, we'll use the same technique. Oh, sorry, there must have been a problem. Okay, so basically we use the same technique and we find the number of times this appears. Oh, I think I know what we're doing wrong. So now we've got a problem. We've got 9, but we're iterating through the list for each 9 value, right? But we only have to do it for one 9 value. So we want to take all of the unique numbers and kind of iterate through all of the unique numbers, see if they're in both lists, and then output our answer. The reason we could use this technique for this one is because there was only one unique number that appeared in both lists. Here we have 2 9s. So why don't we change this to, for I in set R. Set just makes it a unique set of unique elements. So this will only have 8 and 9, because 8 and 9 are the only unique elements. Oh, actually, you know what? We'll keep this as R set. Let's see if this works. Yep, 21. That's our answer. Basically, we're doing the same method, counting the number of times this appears once and once. So 1 times 1 is 1. 4 and 1, 2, 3, 4, 5. 4 times 5 is 20, so 20 plus 1 is 21. That's just our answer. Now, this is all good, but the problem is this can get really slow, especially when we're like reading the values from 2 files. So we want a more elegant way to do that. And this will be called like our brute force solution. Actually, we'll just name this brute force. Right, and let's just comment this. Oopsies. Oh, why is Okay. Now let's do a more elegant solution. This is probably my favorite method. That we'll just go over 1. Actually, we didn't even need to write it elegant solution because we've got it here. Basically, we read in the data, but instead of putting the lines of data into a list, we're going to put them into a dictionary. Now, what this dictionary is going to do is, I'll open a new pane file. What this dictionary is going to do is it's going to hold all of the values and the counts for each of those values. So we've got our Scarlett's Rose's dictionary should have this. And Scarlett's dictionary should have this. Now, what we're going to do is we're going to iterate through this dictionary the keys, and let's see if any of the keys. So we go to 6, 1, 2. 2 is in Rose's dictionary. Now we take the value times this one's value. Now this is much faster, and it actually works. So, but let's see that. So we've got we appended to a new 1 value. Like if it's not in the dictionary already, we set it as value 1. But if it is, we increment the value by 1. Now we do that the same for the Scarlett's one. For each value in the right list in the Rose's dictionary, if this value appears in Scarlett's dictionary, then we increment our answer by the value of the value in Rose's dictionary times the value in Scarlett's dictionary, and then that gives us a much faster solution. Sorry for my poor explanation, but this is just to show how dictionaries, not just dictionaries, but faster solutions can improve programming and time. And the way I'll show you that is if you look at the submissions. I tested quite a few submissions. Here you can see solutions 1 and 2. Can I show the code? Oh, wait. If I show you the source code, I've used the set method where I've created a new set, and then for I in the set, we're gonna do if the value is in our list in Rose's cards and Scarlett's cards, then we times. The problem is, look, we've got it right, but now we're getting suddenly a time limit error because the code runs for more than 1 second. But if we go to our dictionary solution, you can see that, let me just show the code, it's the same as before, but now we're not getting any time limit. The longest it takes to run is 0.118 seconds, which is significantly faster than the list solution. So that's just one way that different data structures or different algorithms can help improve time and elegancy of your code. So thank you for watching.